All right, we talked about series last year in Algebra 2. A series is different from a sequence because a series means you add up all the terms of the sequence.
Amen.
So, a sequence might look like, and I should have said this the other day. These are not the kind of things, those little shiny things that are on girls' dresses.
Oh, I got so confused.
A sequence is completely different than that.
Okay, good.
2, let's say 5, 8, 11, 14. Okay, that's a sequence. A series is 2 plus 5 plus 8 plus 11 plus 14. That's the difference between these two terms. Sequence is a list, series is a sum. Okay, now, we introduced summation notation to you last year, so it should be very familiar to you. I should say it should be familiar to you, maybe not very, but I do need to go over it. So we have the capital Greek letter sigma, which this is telling me to add things up, right? This is the sum formula, or the symbol in math, which is shorthand for adding up a bunch of things.
Yep.
There's an index on the bottom, right? That's called my index. And it's got my starting value. You could think of this like the number that you're plugging in, like an x value. Bad looking up. Oh my goodness, this is horrible. Seriously? Let's get something that's readable. Not much better. And then we have a stopping point. So let's say for this particular group of numbers, we had 5 terms, right? 5 terms. So it has a stopping point of 5. Now, next to that is going to be some sort of explicit formula.
There's bound to be a joke we can make about that.
For this particular function, 2, 5, 8, 11, 14, that's arithmetic. You can tell because there's a constant difference of 3 between the terms. Remember how we take any term minus the previous term, and that tells us the common difference? So the explicit formula for an arithmetic would look like this. First term plus common difference times n minus 1. And that means that the children will be coming soon to my class, so I need to pause this video and come back to it after school when they leave. It's true, folks.
Okay, so what if it were an infinite group of values that was being added together? And what would that look like? So is it possible that I could do n equals 1 to infinity of 2 plus 3 times n minus 1? Is this something that could be written out? Well, I could write it out maybe in an abbreviated fashion. So, for instance, we start with 2 and 5 and 8 and 11, okay? And pretty soon, I'm going to want to stop writing because that thing goes on forever and ever and ever. And so I guess what I want you to notice is that the ... at the end is telling me that it's infinite. Now, if I ever ask you this question, evaluate, I just want you to think about that for a second. Is there a way to add up an infinite group of numbers that are always getting bigger? Answer, no. So there is no sum. You know, if you wanted to use that phrase right there, no sum. So I guess that's kind of a trick question. Now, could I ask you to write it out in terms of its summation notation? Maybe start with this and then go write the summation notation? Sure, I could have you write it out. But if I ever asked you to evaluate it, that would be, in the words of Admiral Akbar from The Return of the Jedi, it's a trap. That's exactly what that is. Okay, there is no sum. Okay. I'm going to tell you a little story about a kid named Carl Gauss. Now, this is, we're talking late 1700s. Carl Gauss, complete genius, and known on the streets as Lil Carl. He's in first grade. He gets in trouble. His teacher says that he has to stay in for recess because he got in trouble. And he has, as a punishment, he has to add the numbers from 1 to 100. Now, little Carl, being the genius that he is, walked up and wrote down 5,050, which is the correct answer. How did this first grade kid figure this out? Well, keep in mind, he is a mathematical genius. I didn't have these kind of thoughts when I was in first grade, and I'm pretty sure most of us don't. That's what separates these kind of people from the rest of us. So this is what he saw. He's adding the numbers from 1 to 100. And so he adds 1 plus 100, and that's 101. And then he added 2 and 99, which is 101. And then he added 3 and 98, which is 101. Oh my goodness, I see a pattern. How many of these pairs of numbers are we going to get? You're going to get 50 of these 101s. Well, that's 5,000 plus another 50. And so that's where this little first grader came up with that. So let's look at what Lil Carl's formula, what he came up with. So the formula for adding up all these terms of an arithmetic, and I should go back and state this. This is finite arithmetic series. Finite arithmetic series. Every time we see a finite arithmetic series, we need to think about Lil Carl. So, Lil Carl's formula looks like this. Whoa, that's a bad looking ant. The number of, maybe I should zoom in a little bit, make it a little easier on myself. The number of terms, that's what the N stands for, right? Number of terms. Times the sum of the first term plus the last term. So we got first term plus last term. Those are the only things we need to know in order to be able to use Lil Carl's formula. If you go to the resource room, they will probably not know what you're talking about when you mention Lil Carl, because those people are not as educated as us bright people. We know what's really going on. So Lil Carl, when you get down there and they talk finite arithmetic series, you mention Lil Carl, they'll know you're from my class. Well, look at that. Now, Lil Carl did have. Now, this is a modified version. I mean, look at this. What are you trying to do? What are you trying to do with that? Are you trying to trick us? Seriously. Okay, we can bring that outside. Okay, I don't know what they're doing there. Unless they're just trying to show you that they averaged. I guess you could look at it as an average of the first and the last term times the number of terms. But, you know, don't try to disguise Little Carl's formula. Now, there is a substitution that we could do right here. We could use the explicit formula for an arithmetic sequence, right? First term plus common difference times n minus 1. That's something that we could substitute in for a sub n. And if you do that, Little Carl did have a cousin. I think his cousin was Merv. But, so cousin Merv would be this one right here. If you take a look at this, so in Little Carl's formula, the n over 2 sits on the outside. If you have an a sub 1, which Little Carl's formula does, and then you substitute this red box in here, there's another a sub 1. So if you have a sub 1 and a sub 1, that makes 2 a sub 1s. And then, of course, you can see the rest of the substitution sitting right there. Now, when would I ever use that? I really don't have to. Okay? You can tell that there's no last term here. So I do include that formula on the formula sheet in case you want to use Cousin Merv, but Lil Carl is just as good. It does all the tricks that you need. You might have to use the explicit formula to find the last term, but that's not really that hard. You are more than capable people. All right. A corner stadium has 8 seats along the front row. Each successive seat has 2 more seats. So it's doing this kind of thing. There are 12 rows, so n is equal to 12. How many seats are in the top row? Okay, so let's see here. We want to know the 12th row, first term, plus, what is the common difference here? Well, it's a positive 2. That's right, any term minus the previous term. Yeah, we could do that. Plus, they told us it has 2 more seats. Anyway, 12 minus 1. So we know that we have, don't you dare add the 8 and the 2 together. Oh, that just hurts me down deep inside when kids do that. Okay, 12 minus 1 is 11, times 2 is 22, plus 8 is 30. Okay, so the 12th row has 30 seats in it. How many are in the entire section? Oh, finite arithmetic series. What does that add up to? Finite plus arithmetic plus series. Lil Carl, that's right, folks. Adds up to Lil Carl. The sum of the 12 terms. Well, we know that we have 6 of those pairs, 12 over 2. The first term is 8. The last term is 30. So we can simplify this, right? 6 times 38. Pull out the handy dandy calculator. 228. I knew you were laughing at my sound effects, not side effects. I'm sure there's side effects too. The side effects of having Mr. Staley as your teacher. Okay. So what happens if it's finite geometric? Woo, finite geometric. What if we're not dealing with arithmetic? What if we're dealing with the geometric? Well, guess what? We got a formula for that too, which we taught you last year. It's not that hard to use. You need to know the first term, you need to know the common ratio, and you need to know how many terms there are. So let's see here. Find the sum of the geometric sequence. Okay, so if I want to know the multiplier, I take any term and I divide by the previous term. Well, back in middle school, I think we taught you that any term, you could change it from division to multiplying by the reciprocal. And so you could find out, oh, look, the 4's cancel out, leaving me negative 1 over 3. So the multiplier is negative 1/3. We can easily tell that the first term is 4. Is that all we need to know? No, we need to know the number of terms. So the last term in our list is this one. Okay, so we know that the formula for a geometric sequence looks something like this. Let me give myself a little bit of space here. And so we have first term, that's 4. Multiplier, we figured out that was negative 1/3. So how do we figure out the number of terms? Well, we take this cool last term in the list and we put it over on this side of the equation. 4 times negative 1/3 to the 10th. Now this happens to be just like the nicest setup for a problem in the world. Look, the bases are the same. The multipliers are the same. What does that mean about the exponents? It means the exponents must be the same. Now, if they're not the same, what do you have to do? You have to divide by 4. And if this wasn't as nice as this is, I know you'll all be screaming at me, but there's only one way to do it: logarithms. Now, why didn't I use logarithms in this particular situation? Because this problem was practically gift-wrapped for me. I mean, they made the last term equal to an equation. They didn't type this on it. If you type this nasty thing on a calculator and give me some weird decimal, you better believe I'm using logarithms to figure that out. Although I would have to take the negative off the multiplier. Oh my goodness. Those nasty people. They made life difficult. So I'd have to take the negative off to even do the problem. So there's 11 terms. So now we have everything we need to know. First term, multiplier, number of terms. So now we can use the sum formula. Sum of 11 terms. First term was a 4. Common multiplier was negative 1/3. Now be careful with this. This is a negative multiplier to the 11th power all over 1 minus negative 1/3. Okay, just be careful on how you're doing this. So the numerator 4 times 1 minus negative 1/3 to the 11th. So I get this really weird decimal, like there's like 4 zeros and a 2258, and of course on the bottom there I've got let's see, 1 plus 1/3, so that's like 4/3. That's kind of ugly. So I end up with a sum of 3.000. In essence, it's just a little over 3. I mean, for all intents and purposes, 3 will be fine. Okay. An infinite series. I mentioned this earlier. Infinite series obviously has an infinite number of terms. Okay. And as I said earlier, an arithmetic one would not be something that ever converges. Okay, let me back up and look at this. What makes series so interesting is sometimes the sequence of partial sums. Now, this term needs to be described to you. What is a partial sum? A partial sum is when we add up a certain number of terms. So like the first partial sum only contains one term, but the second partial sum contains the sum of the first and the second terms. And the third partial sum contains a sub 1, a sub 2, and a sub 3. And the fourth partial sum, I should scoot over just to give myself room, has 1, 2, 3, and 4. The first four terms added up. Now, what's so interesting about that? Well, when we start looking at these partial sums, we can then find out if the partial sums converge. Now, what does converge mean? Converge means gets close to a single number. And diverge means doesn't converge. To be as brief as I can be. Do the partial sums converge? That's the question that they're going to be asking. When we start taking a look at S1 and S2 and S3 and S4 and S5, and then eventually, the limit as n goes to infinity of S sub n. In other words, do these partial sums get closer and closer and closer to a particular value, or do these partial sums not get close to anything? If they get close to something, then the infinite series will converge. And there are the ones we're going to focus on are the easy ones. We're going to focus on geometric ones. But in calculus, they get into ones that are kind of different. We'll look at a couple that are different. For which of the following series, or for each of the following series, find the first terms in the sequence of partial sums. So in other words, like for instance, you know what, let's make a table for a letter. Let's just, I wonder if I could do this. This may not be enough space. So S1, S2, S3, S4, and S5. So the first partial sums, those are the easy ones, right? Because it only has one term in it. But the second partial sum contains two terms. Well, that would be 0.11. And the second would be 30. And the third would be 0. Okay, and then if I go to three terms, 0.111, 60, and 1. Because all I'm doing is I'm doing, you know, I'm up to three terms now. And now I go to the fourth one, add the fourth one in there, 0.1111. Adding 40, I get 100. Adding the next term over, right, I get 0. Adding the fifth one in, 0.11111. Adding 50 would be 150. Adding another 1. So here's what I want to look at. I want to look at these partial sums. What do you think we're getting close to? What do you think the first one's getting close to? I hope you say 0.1 repeating. That's right. As you take the limit, as n goes to infinity, of these partial sums, that's what you're finding right there. Well, if you look at the next one, it's getting huge, and it's just going to keep going. So it doesn't converge like this one. This one converges. I'll use that abbreviation. This one diverges. Now, I hope you understand that means no sum, or no limit in this particular case, which eventually means no sum, basically, because it diverges. It doesn't get close to anything. The limit does not exist. And if you look at the bottom one, 1, 0, 1, 0, 1, 0, it also diverges, right? Because there's no limit that exists there. Because it's not getting close to a single value. It just keeps alternating back and forth. So we can look at partial sums, and there's lots and lots and lots of other weird ones out there to look at. But we're going to specifically focus our attention on the infinite geometric ones. Now, if you know anything, the geometric pattern is exponential growth or decay. So if we're talking about a sequence of numbers that's doing this, that's exponential growth. Is that getting close to anything? Absolutely not. What about exponential decay? Could we be getting close to something? Sure we could be. So what do you know about exponential growth? Well, the multiplier would have to be greater than 1 or equal to. Well, equal to wouldn't be, it'd be pretty flat there. But if the multiplier was greater than or equal to 1, it diverges. Now, why do we have to throw the absolute value bars on there? Because as we might have talked about or seen other examples, there's such a thing as the alternating one, right? Positive, negative, positive, negative. And it's doing this kind of thing where it's getting farther and farther and farther and farther away from 0, but you can see that it's spreading out. The alternate, you got one path that's going up this way and another path that's going down that way. It's not getting close to a single value. Exponential decay. If the absolute value of r is less than 1, then it converges. And if it converges, what does it converge to? We taught you last year that it would converge, the infinite geometric formula would converge to first term over 1 minus r. So, whatever the first term is, I just need the first term and the ratio, and I'm good to go. Determine whether the series converges or diverges. Well, this is definitely a converger, and so is this one, because the multipliers are 1/2, or the absolute value of the multipliers are less than 1. Same thing here, we got a multiplier of 1/2. Pi over 2 is not. 3.14 divided by 2 is 1.57. So this is definitely going to be a diverger. Converge, converge, converge. And we can use the formula on each one of these. And let's see, we could probably do this. At least we can do. Nah, I'm going to save using the formula for in class. So this is where the notes will stop. Or we'll do one. Let's just do one. Yeah, I knew you were like, oh yeah, this is where we get to quit. No. One last thing. So we'll do this one. So the sum of the infinite formula, first term. Well, how do I find the first term? Just plug in the number on the bottom and don't try to get tricked, because I can see that they're going to try to trick me right there on letter B. So if I plug in a 1, 3 times 0.75 to the 1 minus 1 does end up giving me 3. So now we know the first term is 3. Now, if on the next one, when you plug in a 0, you find out that the first term is a 1. So that's where I know. I know on letter B they're going to try to trick me. My multiplier is 0.75, so 3 divided by 0.25, what is that, 12? So my sum is 12, and that'll be it. We'll finish the rest of these in class on Tuesday, or whenever we get together, since I don't know when this will be next year.